Okay, this is number 7, and in number 7 we have a intake manifold where two different water flows are entering in the manifold and one is exiting. And you can see here we've got the different sizes. I'm not drawing these very well, but this D1 is equal to 20 centimeters, D2 is 10 centimeters, and you're given the velocity in both of these being 5 meters per second. And the question is, what is the velocity for the diameter 3, which is 30 centimeters? Okay, so what I hope that you recognize in this particular problem is that this is simply a matter of mass balance. And we know that, as all things, that the mass in is equal to the mass out for a steady state situation. So you'll see this on your the FE materials in here in one-dimensional flow situations, this continuity equation. And you see here that as long as the flow is continuous, we have that A1, V1 equals A2, V2. So, So A1, V1 equals A2, V2. Now, well, in this case, we have two different areas, and coming in. Another way of saying this is that the A in, V in equals A out, V out. So in our case, we have there's going to be A1 here, A2 here, and A3 here. So you notice that, of course, all these are going to have the form of the area equals pi over 4 times d squared. Since every term will have the pi over 4 in it, we'll be able to cancel that out. So let's just write that down. We have pi over 4 as a factor times d1 squared plus d2 squared. Since the velocity, I guess I could have said the velocity. Well, I should probably do it this way. Let me not take any shortcuts. Pi over 4 d1 squared times, that's the area, this is A1, times V1 plus pi over 4 times d2 squared times V2 equals pi over 4 times d3 squared. Again, this is A2. This is A3 times V3. So you can see in this setup, we can cancel this value because it shows up everywhere. And you see V1 is equal to V2. So that leads to the following. We have D1 squared plus D2 squared times the velocity 1, which is 5 meters per second, equals d3 squared times v3, and that is the thing that we are looking for. So let's plug in some of these numbers. D1 squared. Now, once again, if we could convert this to meters, but if we use all centimeters for the d's, then those centimeters will cancel. So let's go ahead and just for simplification. So d1 is 20 squared plus 10 squared times 5 meters per second equals 30 squared times v3. Again, we're searching for v3. So we've got now v3 is equal to 1 over 30 squared is, what is that, 900? Actually, I'm going to take 1 out of 100 times 9, because you can see that I'm going to have 20 squared is going to be 400. It's 4. 10 squared is 100 plus 1 times 100 times 5. So I'm going to go ahead and cancel some of this stuff out, get rid of the hundreds. So we end up getting 4 plus 1 is 5 times 5 is 25. 25 over 9 equals V3. What is 25 over 9? That's 2, and what does that leave me? 2, 8, 6, 8, 2 and 6 ninths, or 2 and Is that right? 18, 25 minus 18 is 25 minus 18. Is that 6? No, that's 7. 2 and 7/9. Okay, that's 2.7 equals V3, 2.7 meters per second. 2.7 meters per second. That's V3. Now let's see if that makes sense. We've got 2 coming in, 1 going out. These are both, this is 5, this is 5. Do we expect this to be smaller? Since the area is larger, and the area goes with d squared. So yes, we expect v to, in fact, since AV in equals AV out, since the area is bigger than this one, we expect the velocity to be smaller. Okay, looks good.